Let's do some two-dimensional elastic collision problems, figure out what variables we have to have, and solve them with just a teeny tiny bit of algebra and no trigonometry. Elastic collisions, where both kinetic energy and momentum are conserved. Now, normally you start out with one-dimensional collisions where you got a track, right? These things are stuck in one dimension, straight line, and then this one gets smacked by that one, and you see what happens, right? So that is one possibility. Now, those require a whole bunch of math, and it is kind of easy if you can get data on those to check and see if momentum and kinetic energy are conserved. And if you do have the magnet-to-magnet ones and the collision isn't too violent and the wheels are pretty good, you do get both momentum and kinetic energy conserved pretty well. If, however, they stick together with the Velcro, right, that's not elastic, perfectly inelastic. You still have some kinetic energy at the end, but a lot of it is lost. Now, those really aren't too exciting. Now, the exciting ones are the fun ones are when you have a ball rolling along and it runs into another ball and the two go off in two different directions. Now these, you start off with two of exactly the same mass, and it turns out because of, well, algebra and trigonometry and right triangles that this and this, if they are the same mass, they will move at right angles to each other. Now those are all right. Now the best ones are if you have one that is one mass and one that is a different unknown mass, and similar to some of the molecular and atomic collisions that you see. So this thing comes in, runs into that thing, and then or this thing comes in, runs into that thing, and then bounces back at some different angle. These are some pretty fascinating collisions. And I just found out that there's a really cool way to find well, if you know the mass and the velocity of this, and you know the final velocity of this, then you can figure out what both the mass and velocity are of this, because you have enough information knowing that it is an elastic collision. You know the kinetic energy and momentum are conserved. You can use triangles and basic calculations for 1/2 mv squared because the total beginning and the total end are exactly the same. Anyway, it's a pretty cool solution, so check this out. We're going to focus on two different mass objects and a two-dimensional collision. Looks complicated now, but you should see the all algebra, all trig solution. Ridiculous. Defining variables, drawing triangles, putting momentum and kinetic energy together. Collisions with the same mass object, whole lot easier to do. We won't be doing those. Instead, two different masses. After trying a bunch of different possibilities, I realized that if I gave myself the mass of both of the objects at the beginning, it was too many restrictions in the problem. If I just don't know the mass of this thing, then the problem is actually solvable and relatively easy using some pretty simple techniques. So here's the situation. I've got a 10 kilogram mass moving at 3 meters per second, striking an unknown mass. That's the before picture, just before the collision. And then just after the collision, the 10 kilogram mass is moving 30 degrees from the original direction of travel at 2 meters per second, and the unknown mass is traveling at some unknown velocity. Because I don't know the mass and I don't know the final velocity of that one, this becomes a solvable problem using the big principle, the law of conservation of momentum. No net external forces, no mass or energy in or out of this collection of two objects. And the total momentum at the beginning, this, which is 30 kilogram meters per second, is equal to the total momentum at the end, which is this plus this. We could do it graphically, geometrically, and first fulfill the condition for elastic collisions of conservation of momentum, but we also know there's a conservation of kinetic energy component because it is an elastic collision. And those elastic collisions, the perfect collisions, both of these conditions must be satisfied. So not only do you have the conservation of momentum, but the kinetic energy is conserved because there's no transformation of one energy to another type of energy, so it all stays kinetic. It's a perfect bounce, works really well for atomic and molecular collisions, doesn't really work. I mean, we pretend it does for pool balls and things like that. The magnet carts, it does a pretty good job of fulfilling these too, but there's still some kinetic energy transformation into other things. through friction, sound, things like that. But anyway, this is an elastic collision, and both momentum and kinetic energy are conserved. So I know that the total momentum of this, that 30 kilogram meters per second, is going to be equal to the sum of those two. So I can draw this. I'm going to make it 15 centimeters long exactly. It's 30 kilogram meters per second representing the left-hand side of this equation, and this whole thing over here, 15 centimeters long, just so I keep my scale in mind. That's how I do these scale things. Now I want the 20 kilogram meters per second is going to be 10 centimeters, 30 degrees. Measure the 30-degree angle, draw the 10 centimeters. It's better on graph paper, but you can see it better if it's on white paper. So measure the 30-degree angle. It's going to be this, that sum is equal to this, which is that one, plus that. And it's this plus that gives me that. So all I have to do now is connect these two and measure the direction and the magnitude. 8.1 centimeters. So here's the momentum. 16.2 kilogram meters per second at 39 degrees is the momentum of that unknown mass. But that's P equals mv, and that leaves me with two unknowns. Both the mass and the velocity are unknown. But I do have a second equation. Oh, check this out. The total kinetic energy at the beginning is equal to the total kinetic energy at the end, which is 1/2 mv squared is equal to 1/2 mv squared plus 1/2 mv squared. I know the mass and velocity. Oh, wait a minute, I got two equations, exactly the same two unknowns. Oh yeah. So 1/2 times the 10 kilograms times 3 meters per second squared plus none is equal to 1/2 times the mass times the speed squared. This is a non-vector equation, a scalar equation, 1/2 mv squared. You see the m and the v, mv, two equations, two unknowns. I can do a substitution and solve for both the mass and the velocity. Put the numbers in. 45 joules equals 20 joules plus 1/2 mv squared. Subtract the 20, get 25. Multiply by 2, you get 50. So mv squared is equal to 50 joules, and mv is equal to 16.2 kilogram meters per second. Take those two, put them together, solve for mass and velocity, then back check. You could also, rather than doing all this algebra using that principle, just calculate the kinetic energy. 1/2 the mass, which is 5, times v squared, 9. 9 times 5 is 45. So you can do this up here, different color pen, 45 joules, 0 joules. And then over here, 10, 1/2 times the mass, 5 times 2 squared, 20. This is 20. 20 joules, and this is 1/2 mv squared. So rather than doing all this algebra here, you can use the principle, look up here at those values for kinetic energy with a different color. 45, we'll subtract 20 is 25. So 25 is equal to 1/2 mv squared. Get down to this point, do some quick algebra, and get that. If you wanted to do a little bit to eliminate some algebra that you see here, because this is annoying for some people. Drop the units because you're not actually following them anyway. So solve for mass. Mass is 16.2 divided by the v, and then substitute in this equation for the mass. So 16.2 over v goes in for that mass. So 50 is equal to 16.2 over v times v squared. That v kills one of these v's, and then take the 50 divided by 16.2 to get a velocity of 3.09 meters per second. We know the direction. It's 39 degrees in the opposite direction from the initial line of travel. So that is one answer. Then you can take this 3.09, substitute back into this. And so m is equal to 16.2 divided by 3.09. And the mass is 5.2 kilograms. 5.2 kilograms. So now I have the mass of 5.2 kilograms for this unknown up here, and the velocity, how fast that thing is going exactly the proper direction. So now let's back check it. 5.2 times 3.09 equals 16.1. It's a little short of the 16.2, but it's all right. So 16.1 kilogram meters per second. Now, using that same mass and velocity, mass of 5.2 kilograms, now the kinetic energy 0.5 times 5.2 kilograms times velocity, speed 3.09 squared equals 24.8, which is just shy of the 25 that we expected. 45 minus the 20 gives you 25. Why is that? Well, that's not a perfect mathematical solution. It's really close, but this 16.2 momentum isn't exactly the correct answer because I sketched it out. And it's really close. You vary on that third digit, which is totally fine. So it's really good, as long as you don't restrict it too much by giving it a mass and make sure that it is an elastic collision. You're good. A little simplification. Take those 4 orange circled numbers, put them all together, left-hand side equals right-hand side, skip some of the algebra written down, and that's it. Try that with all algebra and all trig. It's a messy one. Compare. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.